Hello and welcome. I'm Matt's Amy Ben-Katan, and today we're going to dig into a really foundational concept in engineering mechanics. It seems pretty simple on the surface, but trust me, it's incredibly powerful. We're talking about the principle of transmissibility. So let's jump right in. So here's how we're going to tackle this. First, we'll see why we even need a new principle in the first place. Then we'll get into the official definition, see how it works visually, and this is super important, we'll talk about its limitations. And then, of course, we'll see how this all applies out in the real world. All right, so first things first, why do we even need another principle? Well, up to this point in mechanics, we've mostly been dealing with what we call particles. You know, these little points in space where all the forces meet up. But the real world, it's built with rigid bodies, things that have actual size and shape. And that, well, that changes the game. You probably remember the parallelogram law, right? It's a great way to add forces together, but it has this one really big assumption baked in. It assumes all the forces are acting on a single tiny point, on a particle. But what happens when we're talking about real-world objects? You know, like a bridge girder or an engine block. Does it really matter if you push on it right here versus, say, a little further down? That is the exact question we're going to answer today. And the answer to that question brings us right to our main event, the concept of transmissibility. Okay, so here is the official textbook definition. Let's read it carefully. The conditions of equilibrium or motion of a rigid body will remain unchanged if a force is replaced by another force of the same magnitude and direction acting at a different point, provided they have the same line of action. Phew! Now, that is a mouthful, I know. So let's break down what it's really saying. For this whole principle to be true, three things absolutely have to be met. The new force has to have the exact same magnitude, the same strength. It has to point in the exact same direction, and this is the most important part, it has to stay on the exact same line of action, that imaginary, infinite line that the force travels along. That line of action is really the secret sauce here. So let's spend a minute just visualizing what that means and how this whole thing actually works. Just take a look at this diagram. We've got a force, let's call it F, acting on some kind of rigid body. What the principle is telling us is that we can basically just slide that force along its dashed line of action to a new spot, F'. And as far as the body is concerned, externally, nothing has changed. It won't feel a difference. You know, here's a way to think about it that makes a lot of sense. Imagine a car. If all you care about is making the car move forward, doesn't matter if you push it from the back with 100 pounds of force or if you pull it from the front with 100 pounds of force. The answer is no. The car is going to accelerate in the exact same way. The external effect is identical. Okay, so that might get you thinking, wait a minute. Can I just move a force to any spot on an object and get the same result? And the answer is a big, definite no. This is so important. The force absolutely must stay in its original line of action. The moment you move it off that line, you're doing something totally different. You're actually introducing a tendency for the object to rotate. You're creating a moment, and that changes the entire problem. All right, this leads us to a really important point, a key limitation of this principle. We have to be super clear about the difference between external effects on a body and the internal effects happening inside of it. So let's go back to that car example for a second. Pushing from the back, pulling from the front. Are those two situations exactly the same in every single way? And again, the answer is a big no. Think about what the car's bumper is actually experiencing. When you push on it, you're squishing the material, you're putting it into what we call compression. But when you pull on it, you're stretching it out, you're putting it into tension. So while the car's motion is the same on the outside, what's happening inside the material is completely different. And that right there is the key takeaway. The principle of transmissibility is a fantastic tool, but it's only for analyzing the external effects on a rigid body, things like its overall motion or whether it's in equilibrium. It tells us absolutely nothing about the internal stresses or deformations going on inside. So you might be asking, why does this all matter? Why are we learning this? Well, it matters because it's an incredibly practical tool that engineers use all the time. Let's look at some real-world examples. I mean, this is not just some abstract theory. Engineers rely on this principle every single day. It helps us simplify really complex problems. Think about it. Instead of having to worry about the exact point a cable attaches to a beam, we can just slide that force along the cable's line of action. It makes the math so much cleaner and the analysis so much faster. Okay, let's wrap this up. We'll do a quick summary of the big ideas, and then I'll show you where we're headed next with this. If you remember just one thing from today, please let it be this. A force can be moved anywhere along its line of action without changing the external effects on a rigid body. That one sentence, that idea, is the key to unlocking so much of what we do in engineering analysis. And it's really important that you get comfortable with this idea because it's not a one-off trick. It is a fundamental tool that we are going to use constantly. It's really a cornerstone of statics. And now that we have this amazing tool in our toolbox, we're ready to put it to work. In our next session, we're going to apply this very principle to start solving for equilibrium in real-world rigid body problems. I hope you'll join me. Thanks so much for watching.